Today I'm going to look at sections 5.5 and 5.6, and we're looking at free body diagrams for in 3 dimensions now. Okay, here's two types of supports, and this is a journal bearing, and this is a diagram of a ball and socket. And what you're going to find when you have like a single support like this, the ball and socket type will allow rotation about any axis. What it won't allow is translation. So there's reactive forces, three reactive forces on this, but there are no reactive moments. With a single, this is two journal bearings. With a single bearing like this, what you'll find is that it'll allow rotation just about this axis, but it resists rotation about the other axes. Okay. Now, when you have them like this, and if they're properly aligned, you can actually eliminate those reactions also about those other axes. Only you'll have reactive forces acting on each of these. Okay. Okay. Um, so in order to design these, of course, we need to find the reactions, right? So we need to know something about those reactions. Okay. Here's another example. Same idea. You need to understand the reactions that are provided here, because if, let's say you're to move from point A to point D and you connect this up, you'd have to figure out what the tension in this bar would be, right? So how does it change when you move from point B to point D, okay? And what would be your expectation for that, right? And you could see actually what would you expect? An increase, right? Significantly. So you have to make sure you understand that. The anchor point would have to be stronger. The anchor points on both sides would have to be stronger, and also that the bar itself. Okay. Okay. So here's another application. Now, here's a good question. Be like, how can you determine the largest oil drum weight that the crane can support without overturning? Well, what do we expect that can possibly happen? This part could lift up from point C, could lift up, and this could fall forward, right? So what we have to do is that the center of mass of this G basically represents the center of mass. It looks like in the middle here um, of this crane. If we think about it in terms of like along this plane, and maybe we can make this, since it's symmetric about this line X, we could really just take a look at this as a 2D problem. If this crane is straight along this line, which it looks like it is. And what we would find looking at the side here, so we're looking like the ZX plane from the side, is that if you had developed a moment about this line here, which you could also make it just a point on this axis, if there's a net moment about that point, this would lift up. So you have a reaction due to the mass of this crane that would cause it essentially a reactive moment to stop this from rotating down. You'd have a reaction in the other direction. If this length of this arm increased or the weight of this increased, eventually what would happen is the reaction provided by the weight of this crane in its position would be overcome by the weight and the moment due to this barrel. So it would cause net rotation. Okay, that's how we would do that. Okay. Here's some supports. You could have like a smooth surface support, and then your reaction, of course, would just be straight up. You could have a journal bearing. In this case, you'll notice that it has reactive moments in this direction, this direction. It only allows rotation about along this axis. Okay, if this is the y-axis, let's say. Or actually, yeah. So it would allow rotation about this axis, plus it could slide in and out. Okay, so you have four reactions. Okay, now if you're looking at a single hinge, what you can do here is that, or what you have here is that it allows rotation about the y-axis, but um, there's reactions in all three directions to stop it from moving. So what do we have when we're doing a equilibrium problem? We're drawing the free body diagram. If we have this kind of support, we represent it this way with this reaction, single journal bearing, because if we have properly aligned bearings, we actually get rid of the reactive moments. Um, so then we have, this would be what it would be if you have a journal bearing, and then here's the ball and socket. Of course, the ball and socket is, this thing can rotate around along any axis, it just can't translate one way or the other. Okay? So here's some examples. There's actually in the textbook there are more examples for you to take a look at for there are additional types of supports. Okay? Okay, so general rule or the note you want to take a look at here. So if it prevents translation of body in given direction, then you have a reaction force acting the opposite direction, right? And also rotation. A couple moment is exerted um, at those supports. Okay, if it stops it from moving in that direction. All right. Okay. Here's some other ones. Here's some single bearings and multiple bearings in this case. But a single bearing can prevent rotation, providing a resistive couple moment. Okay. So one of the things we'll look at some more, if you have aligned bearings or hinges, like journal bearings or hinges, you can actually remove the reactive moments. If they're perfectly aligned, one essentially reacts against the other. So together, um, they remove any kind of reactive moment. Okay, so you can handle it like that. So that case, only force reactions are generated, right? Okay, we may look at a problem like that. Okay. Here's our equations of equilibrium. So the 3D, what did it do? Well, we've got all of them are equal to 0. We have the forces in the three directions, and we have the moment about the three moments about each of the axes, and now all equal to 0. Okay. Okay. And when you actually are looking for unknowns, um, if you go to solving the problem where the maximum number of unknown forces are present at a specific point, then typically if you use that as your point to do a moment, write a moment equation, it's usually easier to solve the problem. So if we were looking back at a problem, let's say we're looking at this one, and this is your free body diagram for that problem. You notice that we have one, two, three forces right here. We would probably the best thing to do would be write a moment equation about this point, okay? Because we have three. This one also would be probably about C. That would make it simpler. So if you're writing a moment equation trying to solve for some unknowns, typically the easiest thing would be to write it about point C in this problem. Okay? In this one, C, B, A are all the same. And this is actually like an example here of perfectly aligned ones because now you have you have multiple bearings, so you have no reactive moments about these. And the same thing with this one. Okay, and this is just a single one, so this is you would have reactions about that. So if these are considered to be perfectly aligned, there are no reactive moments about those. Okay. Okay, and that's good for this section.